Okay, thank you. For me, the honor to do the last talk here. It's nice to be able to do that just after Marcus introduced us to the concept of nodes. And when you have lots of nodes, you want to be able to transform them in other kinds of things. And that's what we'll talk about here, the translator language. We use a language for that. But first I will talk a little bit, this is only one sheet, about our environment where we are working. We work at the Dutch text office, and we have been using MPS since 2014. We had a proprietary language workbench, which was almost breaking down. So we had to replace it with something else, and we selected MPS. So since 2014, we're working with model-driven, with MPS, actually. We do model-driven stuff even before that. But the first few years, we did the migration to MPS, and after that, not a lot happened until we started working at a different department at the tax authority and built a tool which we now call ALEF, the Agile Law Execution Factory, which is a tool which in which we can represent in controlled natural language the rules of the law, and then we generate the code that executes that law. We started with that in 2016, and after a few years we started making more and more services. Currently we have about 45 services which are in production and are built using ALEF, and we have more than 100 people trained in using ALEF, so that's quite successful. And actually, this is a promising way to make the tax authority a little bit more flexible in future to be able to implement new tax laws, which is quite a problem at the moment, using the old technology. But now I will talk about the translator languages with nothing to do with taxes, except that we use it, of course. The translator languages was built mainly by Wim Bast. He's also here from the Modeling Value Group, but he's no longer working for us anymore, and we are still building on it and making changes to it. Well, what is a translator language? Well, basically, it's a language with which we make translators, and but what it boils down to is that we need something that does polymorphic dispatch for us and memoization. And if you have these two, it becomes a lot easier to make model-to-model transformations. We apply it for making interpreters, we apply it for doing migrations, for desugaring. Before we do an actual generation step, we do some desugaring sometimes. And currently we are also implementing our type system using this same language. So model-to-model transformation usually entails that you have to do lots of type checks, like is it an instance of a plus expression, then I need to do that. Is it an instance of something else, then I need to do that, etc., etc. And typically you can use a visitor pattern for that or something else. But then you also need to be able to remember what the result of a transformation step was, so that you can make references to the generated node, to the transformed node. And that is a problem in the generator, for instance, that's handled using mapping labels, but it's something that you always need to do when you make transformations. You need to remember the relationship between the source node and the target node, so that you can make a reference to the target node when you know that it was somehow related to this source node somewhere. So, and we can now abstract away from that using our language, translator language. And another thing is that sometimes we made these transformations using just a set of behavior methods, and you can, for every concept and subconcept, you can just re-implement all kinds of virtual methods. But we have many different transformations, and if you put them all in the behavior aspect, we get loads and loads of methods in the behavior, and it's not clear which methods belong to which translator. So that's also an advantage of the translators. So this is the first example of the syntax of our translator language. It's an extension of base language, and a translator is just translated into a class. But a class with a number of methods, but these methods have a different syntax than a normal base language method. They use these double square brackets to enclose their arguments, and you have a return type and a body. So you could just as well do it differently, but these mappings, we call these mappings, they don't have a name. So they're all nameless methods, basically. And so in the top we have there an expression rule that says, okay, any expression is translated to 0. Any variable reference is translated to 1, and every binary operation just adds the translations for both of the arguments of the binary operation. So this basically counts the number of variable references within an expression. So it only it goes down in every sub-expression until you reach a variable reference, and then it counts that. So if you pass this, if you call this method using some expression, it will just look if it is a binary expression, and then it just recursively calls itself again. So the method is actually called depends on the runtime type of the argument that is given to it. Yeah. So when you call a method, so for instance, these other two left and right expressions, square brackets, that's a call to the method, but you don't know which of these three methods is actually called. That's determined by the translator language itself. Is that clear? Yeah, okay. Then, yes. Yeah. We have multi-dispatcher. If you have more than one argument to this mapping labels, then it first tries to focus the most specific left argument, and if there are multiple of those, it tries to find the most specific second argument, etc., until it has selected a right mapping. So, for instance, this is a small expression language that you could see it as a very small specification of an interpreter. If you so for an integer constant, you just return the value of that thing. For a string literal, you return a string, and basically every step here is just a specification of what the semantics of the argument is. But sometimes you need to dispatch based on the argument type. For instance, for a binary operation, you would like to call different mappings depending on the type of the left and right argument. You just do that by adding some additional arguments on which you can then dispatch the method selection on. So, yeah, maybe it's nice if I just show you how this works in MPS. Wrong one. Oh, here. So this is a calculator that I've made using this translator. The translator has a different aspect within. Is this large enough, or should I increase the size a little bit? Yeah. Let's see, how do I do that again? On a Mac, I'm not using a Mac for very long, so can you give me the keystrokes that I need to type to enlarge it a little bit? Oh yeah, that's, no, the mouse doesn't work. Yeah. Oh yeah. Yeah. Edit font is better. Is this large enough? No, okay. So this is just an editor for the calculator. It has an expression. This is base language expression, and after it is the interpreted result. And the translator there is, well, the code that I just showed you on the sheet. But we can actually also make nested translators. That's what we do here for a plus operation. We can define a few rules that are used when you explicitly call that one, but the recursive calls in here, which are absent, would be referring to the plus expression itself. Okay. Just to show you that it actually works, I can put different results, and you get the result from a floating point operation, which is of course a little bit what you wouldn't want there, but well. So you could just change the expression and it changes the result after it. The translator is constantly called in here because the editor just says I have a rule that shows that, and then it just also works. So it starts at the beginning. So this is the sheet that it was. So I explained already, but if you have this memoization, it causes basically that every call to this translator, if it has the same arguments as the previous call, then it will also use a cached value. So it always gets exactly the same result as the previous call. And therefore, if you translate something, then it's very easy to make a reference to that same node that has been generated, but you just call it again, and then it gives the same thing, and that they make that the target of the reference, then it works. So that's, you don't need mapping labels anymore. It's just calling the same thing again, and you'll get the same result. So you don't have to worry that it takes a number, the computation have to be done again because it's cached. So it's in the memoization, causes these circular structures to be circular and not what you would normally have if these were just methods. They would just create a new thing again. So that's a very crucial aspect of this language. Then it has also got automatic lifting. So that basically means that if you have an argument that's just a list of things, then it also looks whether there is something that is just an element of that thing, and then it will call that multiple times and then returns a list of those things. So basically, if you have this code for a summation that has a number of terms that needs to be added together, then you can just call the whole list of terms, and it will automatically apply that to all those things. So you don't have to say select the mapping call on each individual argument, and that gives you a sequence again over which you can fold, but you can do that immediately. Another very useful thing is that you can add guards to these methods. So you can add conditions basically that tell you in which cases these mappings are can be used or not. And if it's not a valid mapping, the guard returns false, then it will just find another method that another mapping that fits the runtime arguments. So you can, for instance, check if one of the arguments is null, and then it will be applied, or not, or all kinds of checks you can do there. And so this is very crucial, because sometimes if you would just put these conditions inside the body of this translator mapping, then it already chose the most specific method, and you cannot escape that anymore. Now, what do we use it for? Now, for instance, for deshubering, we have basically a very generic way of copying a node using this translator language. It just makes a new instance, copies all the properties, copies all the children, and copies all the references. And that is the generic way to copy a node. And then you can make specific rules for specific things that you want to replace by something else. And you can just call the translator on the root node, and it will automatically find the places where things need to be changed. So, for instance, I have here a deshubering for a new concept that's added to the base language that allows you to declare a local variable with the word debug in front of it. And then it will automatically add logging to every access to this thing. And you can do that by just adding this concept, and which is a debug variable is a subclass of a local variable declaration. So you just copy that thing to a local variable declaration. So you remove the debug aspect of it, and you replace it in every reference to it and every assignment to it by adding a closure that does the system out print line of the value of the variable, and then just returns the value, and when you assign it, it just adds the system out print line statement. So this actually also works in MPS. I could show that. So here we have the call of the desugar operation. It just says if it's a root node, then remove that root node and replace it by its desugaring, and otherwise you can replace it in line. The desugaring translator is here, and that contains these few rules that you have there. And then I can just call this. I'll first show you the console output, which contains also stack traces, but you're probably used to that. So now we call it again, and then it has done some system out print lines of this method, which I should have shown before. Let me see. Oh yeah. So I have this small piece of base language code which has this debug local variable in it, and every time that it checks whether it's still smaller than 1,000, or when it multiplies it by 2, that is printed on the system out print line here. So it reads 16 and it reads 16 again, and then it assigns 32 and it reads it twice. And so that is, so it's really just a matter of describing what you want to change, and you don't have to hassle anything with hash maps or to remember what you have generated before. It's just done like this. Back to the presentation. Is there a way to jump into the thing from this sheet? Yeah, well, I'll just do this a few times. So we already showed you, but you can also have you can modularize the translators by making nested translators, and you can override these in subtranslators, etc. Just to put specific mapping rules in separate parts of the translator. So, and you can make different translators and make them cooperate together. You can have a calculator, which I showed you, but we can also make a scientific calculator, which has more operations, for instance, and you just add mapping rules for the extended language in that way. We can make translators that have parameters so that they can communicate with each other through those parameters. And another thing is that if you have translators that inherit from other translators, then you sometimes want to call a translator, but you know that from the very high level language. So you want to construct a translator there. But there are all kinds of extensions, and you would actually want the extensions also to be executed. So you then cannot just create a new instance of the translator. You have to make an instance of a very specific translator. And for that, we can have dynamic translator construction. Oh, I forgot the order of my sheets. So here this is the extension that can extend floating point constants. For instance, for a calculator that was not designed for these things, you can just add them and add rules for the extensions only. And it's just so that the plus nested translator in the previous sheet is now extended with 2 more rules just for these operations. And when you want to construct these translators, you can do that like a normal class construction in base language, like new calculator, if you know exactly the type that you need to have. But you can also do this new calculator with a model before it and a dot expression. And then it will look if in that model there are used languages or solutions that contain translators which are more specific versions of the calculator, and then it will actually make a translator that is that's in there. That's currently still under development, but because there can be more than one most specific extension of the calculator, but that's something we're working on. Yeah. Okay, we can also use this for interpreters. And for that, we have made a whole set of generic model basically for the execution of program containing things like objects. Objects can have slots, and slots can have values. And we have done that in a generic way. And the interpreter mappings just specify, like the ones that I showed you before, how these things need to be translated. But because we can use this generic interface. I think I've shown that in, yeah. This is just an overview of the kind of concepts that are in that interface, but by implementing these interfaces in your language, so certain content have a role like an action, and other have a role like a class or a construction or a value. Literals, for instance, are values, and so we can, and then even though the translator doesn't refer to any of these things, you can. It has a way to look which mappings are actually called, and you can then intersperse all kinds of functionality. We have, for instance, done a coverage tracing with that. We have a debugger. It just builds a new node structure depending on what it sees that is, which mappings are called. Because you can see whether the arguments are then implementing these interfaces. You can make a fully generic debugger and several interpreters that use different languages perhaps, but still can use the same debugger. Well, I'm a bit earlier than I thought I would be, but this was my last sheet, so if there are any questions, then we can, otherwise we can go a little bit earlier to lunch. Yes.
Are there any plans for making this open source?
I knew this question would come. Yes, the plans are there. But yeah.
Can you be a bit more specific about the plans and maybe estimates?
It's obvious that we should make this open source, and but it's the point is we have so many other work to do that somehow we have not yet come so to do it. But we actually we've also got plans to make whole Aleph open source, but that will take a little bit longer. Certainly not this year yet, but yeah.
In fact, by European law, it's illegal to not make it open source.
Yes. Actually, our government has said that all government software should be open source, but well, our organization is suffering from what we call in Dutch cold water fear, and so, but nevertheless, we are making steps, but it goes slowly. Yeah.
I also have a serious question, about the topic itself. What happens with incomplete translators? So if you have a translator that does not have mappings for every combination of input parameters.
And in that case, it will throw an exception telling you that a mapping for a certain argument set is missing. So,
are there ways to detect that might be the case by enumerating all combinations of
oh yeah, it's a model check, you mean? Yeah, that could be done, but we haven't made that yet. No. So usually, what we do is either we make a very high level mapping rule that takes the default case, or we leave that open and make it abstract. So we can also make abstract mappings, and then it will give these exceptions. Yeah.
Okay, thanks.
Nico? For the interpreter, does it always re-evaluate everything, or only so when you call it, it's a complete re-evaluation, or do you do any the memoization could
you can we can define which memo. Actually, it's an argument to the mapping call where you make it, and so you can reuse a memoization of earlier things if
okay, so
that's appropriate. Yeah.
Okay, and then I was thinking about the debugging, right? If you do partial evaluation, then it's pretty hard to predict when you would actually hit a breakpoint.
Hit a breakpoint.
You said you
Yeah,
saw
but
the
our debugger actually just records a trace of everything that's
Okay,
done.
so it's a tracer, not a
Yeah,
debugger.
and then you can then afterwards look where which results came from and drill down into that and do that kind of things. Yeah.
Okay.
So we don't have breakpoints where we stop the interpreter. Yeah.
Any more questions? No? Thank you.
Okay.